Welcome back. We're still discussing the law of conservation of mass in the context of chemical reaction. We want to also appreciate the fact that, in any chemical change, the number of atoms remains constant. The mass, total mass of the reactants needs to be equal to the total mass of the products. So as a result, we want to think of it in terms of saying whatever we put in terms of quantity needs to be equal to what we get out, in relation to the big question that we asked when we said, okay, what exactly happens to the quantity of matter during a chemical change or a chemical reaction? Right. Now let's look at the law of constant composition. Now, in terms of the law of constant composition, this refers, to the particles of which a substance is made up of. Now, if we talk about composition of a pure substance, usually we're talking about compounds, okay? Because we know there are two types of, pure substances. Compounds. Why compounds? We can talk about composition of a compound because it is actually made up of two or more, elements of different types. So as a result, if we talk about composition, we are saying what are these particles that actually make up these pure substances, okay? So different samples of a pure substances, which is a compound, always contains the same element in the same proportion. So for argument's sake, we can talk about, for argument's sake, copper sulfate as a compound, all right? Now, this copper sulfate contains copper, sulfur and oxygen in the ratio 1:1:4. Okay, so that's the proportion of copper, that's the sulfur, and then that's the oxygen. So this is what it means when we say different samples. And when we talk about different samples, we're saying, given a sample of a copper sulfate as an example, these elements that make up copper sulfate will be in the same proportion or same ratio, right? So these elements are always present in the same definite mass, okay, ratio in a compound, irrespective of where the substance is made or found. So even in a mixture, copper sulfate, if it's part of the mixture, these substances or these elements that make up copper sulfate will actually be in the same ratio in terms of mass, or the number of atoms, per sample, right? Okay. Now, if we are to apply the law of constant proportion, okay, there needs to be a consistent chemical formula. So when we talk about chemical formula, which is a very, very important, a part of pre-knowledge or something that we already know or that we need to remind ourselves of, chemical formula, everything starts from the chemical formula. So the chemical formula needs to be correct so that we can able to verify that indeed in different samples of the same substance, these elements that make up that pure substance actually in the same proportion or same ratio, right? Okay, now in terms of applying the law of conservation of mass, we need also to realize that there is consistency in terms of the mass of each substance per formula unit or per unit of a covalent compound. And then it says here the periodic table gives us the relative measurements, okay, of the mass of different atoms. So the periodic table of elements becomes our point of reference when we talk about the relative measurement. And this relative measurement is what we refer to as the relative atomic mass or relative formula mass of different substances, okay? So when we talk about the relative atomic mass, okay, this has to do with the standard reference of the carbon-12. So the carbon-12 is actually our reference element. Everything is made in comparison with the carbon, okay? Now, each carbon atom has 6 protons, and these 6 protons is actually the atomic number, okay? So this is our atomic number, okay? Now, and also 6 neutrons. So if you add the protons and the neutrons, then you get your nucleon number or the mass number, okay? This is what we call the mass number. So all these are actually indicated in the periodic table. So you'll have your symbol C, and then you'll have your atomic number, which is 6, and your mass number, which is 12. This is for carbon 12, okay? Because there are different atoms of the same element that can have the same atomic number but different atomic mass, which we would call isotopes. But for carbon 12, to be specific, this is our atomic number, okay? Okay, this is the number of protons, or the proton number, and then this is our mass number, okay? Right, okay. So in short, as a method of measurement, we would call this 12, which is the nucleon number, as the 12 atomic mass units. So these are the units that we use. We call them the atomic mass units of an element. So we would get these from the periodic table of elements, which is actually that value there next to that symbol, right? Okay. Now, so if we talk about the relative atomic mass of carbon 12, we would say that its relative atomic mass is 12 atomic mass unit. If we talk, for argument's sake, of hydrogen, which is element number 1, it got 1 proton, so its atomic mass unit is also 1. Okay, so the periodic table does provide all this very important information. But if we talk about a molecule of hydrogen, and we know a molecule of hydrogen, we've made examples, which is H2, consists of 2 atoms of the same kind, hence it will be 2 atomic mass units per molecule, which is different from an atom, which consists of a single particle. Okay. Now we talk of also oxygen, which is another diatomic element. It will be 16. 16 comes from 8, per atom, and then there's 2 of them, which gives us 16 atomic mass unit. Then we talk of oxygen molecule, which is actually 32. Right. Okay. And then we also understand that the relative formula mass, which is, this is the symbol of relative molecular mass of a compound. And we talk about formula mass of a compound as the sum, okay, of the different relative atomic mass of, the different atoms that make up that molecule. It can be a molecule of a covalent compound or a formula unit of an ionic compound. Very, very important. So to get the molar mass of, let's say, for argument's sake, relative molecular mass, Mr, let's say, of copper sulfate, for argument's sake, it will be the atomic mass of copper, okay, plus the relative atomic mass of sulfur, okay, right, plus the relative atomic mass of oxygen, right? Very important, okay? Right, and then if you are to use an example of water, it will be, in this case, take note that the formula of water is H2O, okay? It means per molecule of water, there's 2 hydrogen atoms for every atom of oxygen. So then if each hydrogen atom has an atomic mass of 1, then we'd multiply that by 2. Then the total, in terms of the relative formula mass of water, will be 18, okay? Because this is a compound, right? So we'd use the individual relative atomic masses of the elements that make up that particular compound. Because we've already spoken about, composition, law of constant composition. It means that for every molecule of water, there is a constant ratio of hydrogen to oxygen per particle of that particular substance, right? Okay, then we can also look at other different ones, like, let's say, for argument's sake, calcium carbonate, which consists of calcium, which has got a mass of 40. So the relative atomic mass of calcium is 40. We'd get that from the periodic table, okay? And then carbon is 12. We have seen that. So that's the relative atomic mass of carbon, okay? And then 16 is the relative atomic mass of oxygen. But there is 3 atoms of oxygen for every formula unit of calcium carbonate. Hence, the formula mass of calcium carbonate is 100 atomic mass units, okay? Right, now, let's look at the issue of, applying the conservation of mass and atoms. Now, I want us to look at this in terms of, a simulation to see exactly how then we talk about, the number of atoms are remaining constant. Right. Okay. So in our simulation here, we'll look at an example which involves the breaking down of a water molecule. We can put, a certain number of molecules of water that we can break down. So in this case, if we've got one water molecule, obviously you can see that the breaking down does not take place. We need a certain minimum number of water molecules for them to able to be broken down. So we are going to separate water molecules, okay, and see what happens if we do that, okay? Right. So say for argument's sake, we've got, two water molecules, right? So if we've got two water molecules, how many atoms of oxygen are there? There is 2 of them, and then 4 of hydrogen. Okay. So if for argument's sake, we remember the number of atoms on the reactants must equal to those of the product. So for us to balance that, we can go ahead and say, okay, if we have, for argument's sake, 2, how many of these oxygen molecules do we have there? Okay, we still have a lot there. So if we do that, if we start with the water molecules, there's 2 water molecules there, and each molecule has got 1 atom of oxygen and 2 atoms of hydrogen, okay? Now, what do we need to do? We can say, okay, what if we have got, from the number of atoms on the left, if we can count the orange one, there's 2 on the left, there's also 2 on the right. So if we've got 2 molecules of water, from there we can get a molecule of oxygen, which is why the equation is balanced. So the number of atoms of hydrogen on the left-hand side also equals the number of atoms of oxygen oxygen on the right. The same happens with hydrogen. So in other words, we are saying that the total mass does remain constant, right? This is as far as an example, but we can have multiples of them. But what is important is that these chemical change, they actually occur in fixed proportions or in fixed ratio. For every 2 molecules of water, we'll get a molecule of oxygen and 2 molecules of hydrogen. So that's as far as the balancing is concerned as an example, right? Okay. Now, so if we've got 36 grams of water, okay, what do we have on the other side? We can have 2 multiplied by 2 of hydrogen plus 16 multiplied by 2. Now, 16, remember, is the molar mass, atomic mass of a single oxygen atom. So to prove that indeed mass is conserved in as far as also the atoms, we'll have 4 plus 32. Okay, so this 4 plus 32 is actually 36 grams. So that's what we mean when we say mass is conserved during a chemical change, right? So if we've got 2, we'll have for every 2 molecules of water, there are 2 atoms of hydrogen, of oxygen rather, which makes a molecule. So even if you check, it would also give us the same. So if we break this down, every 18 grams of water and 2 grams of hydrogen plus 16 grams of oxygen. So these are the fixed masses in which they react. But also what is important is the constant ratio in which this happens, okay? Right, so we have looked at that simulation. We can also do the same with other substances, but this is just an example that we want to look at. And then also, what is also important in summary is that there is the law of constant proportion. What does that say? That the elements are always present in the same substance in definite mass ratio of the compound, irrespective where that element is actually found. Okay, and also the sum of masses of the reactant is equal to the sum of masses of the products, and the number of atoms is also conserved. Right. So that's as far as the law of conservation of mass, to say that in any chemical change, the total mass of reactants equals to the total mass of the product. With that said, we shall call it a day for now.